Hello everyone, welcome to the Material Science class, Make 300. This is chapter 4, Imperfections in Solids. So this is the title of the chapter. The objective of this chapter 4 is to discuss how the material properties would be related to the imperfections or the defects that would be exist inside the material microstructure or the material structure in general. We said that over chapter 1 that the material has multiple structures or different structures. We have the macroscopic structure, we have the microstructure, which represent the microscopic things that located inside the material structure. Also, we discussed that we do have atomic structure. In chapter 2, we discussed the forces that would be generated between atoms, which something related to the atomic structure of the material. Then in chapter 3, we discussed the atomic structure of a crystalline solid. We said that a crystalline material is the one that has crystals. A crystal, it is a well-defined arrangement of atoms. A crystal, it is a perfect form of the material. A crystal atoms, inside the crystal, they are well arranged. They do have a definite and a specific arrangement. There is no changes. There is no randomness in the distribution of atoms. Atoms are perfectly arranged to form a specific shape, a specific structure known as the crystal structure, which can be represented as a unit cell. We discussed that we do have FCC crystal structure, we do have BCC crystal structure, HCB, and we do have so many crystal systems or different types of crystal structures. So again, this crystal structure is a perfect, this is the ideal condition of the material. This is the best form of the material that we can experience. That we do have these atoms, like the FCC crystal structure, at every corner we do have an atom at the center, exactly at the center of the face. There is an atom, and so on. So we're going to end up with the FCC crystal structure. So it is a perfect thing, ideal thing. This is in chapter 3. Even we have discussed how some of the physical properties, especially the physical property like the density, could be related to this crystal structure. But the question is, are these materials, in reality, these natural material, whatever, metals, ceramics, or polymers even, especially the metals, since we said that all metals are crystalline materials. So are these all metals are perfect with this perfect and ideal crystal structure that we discussed over the chapter 3? No. In many of the cases, there are some imperfections. Imperfection, it is a defect. It is something wrong inside the material microstructure. It is something that is disturbing the atomic arrangement. This atomic arrangement, it will be disordered because of some defects or some imperfection. So generally speaking, this imperfection, this is like a defect inside the material. It is a difference between the ideal image and view of the material to the real material. Real material has defects, whatever it is. So the objective, why we should study this imperfection and what is the importance of these imperfections in this course. Some of the material properties, in fact, many of them, especially the mechanical material properties, are strongly influenced or related to the presence of imperfections inside the material structure. Some of these imperfections could be located at the atomic scale. Some other imperfections could be located at the micro scale. We said that we have different levels of the material structure. We do have macrostructure, microstructure, nanostructure, atomic structure. So some of these imperfections, some of these problems or defects would be related at the atomic scale, at the nanoscale, the micro scale of the material. Even there are some other defects which would be seen in the microscopic scale, but this is not the concern of the material science course. So we're going to focus here on any imperfection, whatever it is, and how the material properties could be affected or influenced by this imperfection or this defect inside the material structure. This is the objective of chapter 4. So in addition, the microstructure of the material, it is not ideal all the time as we imagine. This ideal thing of the material microstructure or even atomic structure, it is not possible. And in most cases, you could say in all cases of the material, especially metals, it contains imperfection. There is no 100% a pure metallic material. There is no 100% perfect material. Anyway, there should be some defects, and definitely these defects will significantly influence the properties of this material. So as we mentioned, the objective of this course is to try to connect anything that is located inside the material microstructure or the material structure to the material properties. How the atomic structure would influence the material properties, how the forces between atoms would influence the material properties, how these imperfections could influence the material properties. This is the objective of chapter 4, is to connect the material properties to these imperfections, and even this will be further discussed over the next chapters. So consequently, it is important to have a knowledge about the types of imperfections. How many, what are the general types of imperfection that would be formed inside the material structure, that would exist in a material microstructure, and know the roles that they play in affecting the behavior of the material or the properties, how the material properties could be related to this imperfection. Again, this is the objective and the importance of this chapter. These things that we are going to discuss here depends on the chapter 3. Chapter 3, we discuss the crystal structure, the different types of crystal structures, how the density could be related. So these imperfections are changes over the ideal crystal structure that we discussed in chapter 3. Chapter 3, we were assuming that the material is ideal. Now, there are some imperfections, there are some defects, there are some changes over this ideal condition of the crystal structure. How these changes would influence the material properties, this is the objective of chapter 4. Make sense? So what is the imperfection? Simply, we can understand the imperfection as a defect in the crystal structure. Anything that is irregular or that is different than the regular structure that we knew about the crystal or the material structure, the atomic structure, it will be counted as a defect, it will be counted as imperfection. So generally, we can define imperfection as a crystalline defect or a crystal defect, which is a lattice irregularity having one or more of its dimensions on the order of an atomic diameter. So what does it mean? What does it mean, the last statement? So first of all, it is crystalline defect. As we mentioned, it is any defect within the regular form of the crystal that we knew as we discussed in the chapter 3. Like for example, in case that you'd have FCC crystal and for some reason one of the atoms that should be located at the corner is not there. So this is a defect. The regular structure of the FCC crystal, there should be an atom at every corner and an atom at the center of every face. So for some reason, if there is one of these atoms is not in its position or shifted or totally completely removed, it means that there is a defect. This is an imperfection in this crystal structure. This imperfection, it could be related to a lattice irregularity having one or more of its dimensions on the order of an atomic diameter. So what does it mean? It means that, for example, in the FCC crystal structure, I could remove only one atom. So it means that this irregularity is atomic. What does it mean atomic? It is related to the one atom. So it has an order of one atomic diameter. Or you could remove, for example, like 10 atoms. So it will have the order of 10 orders of atomic diameter and so on. It means that the defect, it could be related to the atom by removing atoms, or it could be related to the removal of an entire plane of atoms. We discussed the crystallographic planes in chapter 3, and we said that this crystallographic plane represents a plane of atoms. Like you do have an entire plane within the crystal structure has been removed or shifted or displaced right up or down or left. It means that this will be a defect, but this defect is related to a plane of atom, not just one atom, but it is a plane of atom. So anyway, the defect, it is related to one or more dimension, and the size of this defect, it can be counted as multiple orders of the atomic diameter or multiple orders of the atoms. So what are the different types of imperfections? We do have three groups of imperfections. Some of them are point defects, some are line defects, some are planar defects. These different types of defects will be covered and discussed in detail through this chapter. So what is the difference between point, line, and planar? Point, it means that the defect is related to one atom that is not located in its position. Or it is related to one atom, wherever it is located, another atom inserted in a position which it shouldn't be there. So any irregularity in the atomic structure, in the distribution of the atom, it is counted as point defect. Point As you remember in chapter 3, we discussed the crystallographic points. And we said that the points refer to the location of the atom. Like you're going to have one atom that it should be here, but for some reason it has been moved, or it has been entirely removed. So it is a defect, but it is related to one atom which is not there. So it is counted as point. It means that this point that referred to this atom has been removed, so it is a point defect. We may have some atoms that would be removed entirely from the crystal structure, so this would result in a vacancy atoms. So the vacancy atoms, this is one of the defects. What is the type of this defect? It is point defect. It is related to one atom which is not there. Or interstitial atoms. Interstitial atoms, it means that you are going to insert some atoms and force some atoms to be inserted into between the lattices or the spaces between atoms, as it's going to be explained through this video. But the interstitial atom is one of the point defects. Substitutional atoms also one of these defects. All of these three types of defects, these are three types of defects, all of them are counted as point defects related to one atom which is not there, inserted atom. We are going to discuss these defects in detail. There are some other defects which are counted as linear or related to a line of atom, or to be more accurate, to a plane of atom. As we mentioned that the defect, it could be related to one atom, two atoms, three atoms, so it is countable thing. Or it could be related to a plane of atom. In case that you have a plane of atom that has been shifted or moved or whatever, it means that the defect is related to a distortion in this atom, or that this plane of atom has been moved. This is counted as line or linear defect, or line defect. The most common type of line defect is the dislocation, and this is very important. But there are some other type, but the dislocation, it is the key type of defect that is counted as line defect. There are also other types of defects which are related as surface defects or planar defects. Like you're going to have a surface, a group of atoms that is going to form a surface. This surface has some defects. So the defect in this surface will be counted as surface defect or planar defect. The most common type of these planar defects are the grain boundaries. But in addition to the grain boundaries, the dislocation, we do have twinning, we do have so other, for example, lattice strain. So we do have so many types of imperfections, but these are the most common ones. And that's why these are the types of imperfection that we are going to focus on through this chapter. Make sense? So what is the vacancy atom? This is the first time. So let us focus over the point defects. Let's start with the vacancy atom. This is the first imperfection which is counted as a point defect. So a vacancy is one of the point defects that involves a missing atom. That there should be an atom located at this lattice site. Lattice site, which is a position or a location that belongs to an atom. So the lattice site, it is a position or a location that belongs to an atom or a unit cell. Or let us focus as an atom. Like there should be an atom here, so there should be a lattice site that is reserved or devoted for this atom, that is given to this atom, but for some reason this atom is missing, is not there. For some reason, forget about the reason that there is a missing atom, so this will be counted as a vacancy. So the vacancy atoms, it means that the atom is not there. It is not in its location. So it is a missing lattice site or a missing atom or vacant atomic lattice or lattice site in the crystal structure. All crystalline solids contain vacancies. And in fact, it is not possible to create such a material that is free of these defects. The vacancies, this is anyway, any material, whatever it is, definitely it will have some vacancies. It means that there should be, it will have some defects. And this defect will be definitely vacancy atoms. It is hard, it is difficult to have this ideal material that has all the atoms located at their sites and there is no vacant atoms. Vacant atoms, it means missing atoms. No, definitely there are some atoms who are missing within the crystal structure of this material. Whatever the count of this atom is, but anyway, there should be some vacancies. This is what is happening in any real material, whatever it is. So all crystalline solids, whatever they are, metallic, ceramic, even some of the polymers, or any crystalline solid will contain a certain number of vacant atoms or vacancies which is it is impossible to have any material that is free of this defect. So as shown here, what is the problem with this defect? Why this missing atom is counted as a defect? Because, for example, as shown in this graph here, there should be an atom. As you can see, we do have one atom, and there should be another atom here, like this one, and this one, and this one. So there is a missing atom, so this will be counted as a vacancy. Vacancy, it means that this site is empty. This site should be filled with an atom, but for some reason this atom is missing. So it is a vacant atom. It is a vacant lattice site. What is the problem? The problem is because there is no atom here, or this atom has been removed from this ideal crystal structure, this crystal structure will be distorted. Distorted how? For example, this atom will come close to the other atom. This will result in a distortion in the plane. If the atom is already there, this plane will remain straight, this plane will be straight, this plane of atom will be straight, this plane of atom will be straight. All of these planes of the atoms will be perfect, will be completely straight. But what is happening here, because we removed intentionally by enforce, it is not possible even, anyway this vacancy will be there. It means that anyway you're going to end up with some distortion in this plane. This is the vacancy atom. Interstitial atom, I'm going to skip this one for now, then I'm going to move to the interstitial atom, which is this one. Like for example, we may have self-interstitials. What does it mean, self-interstitial? It means that you're going to enforce an atom to be squeezed between the different lattice sites. So again, the difference between the vacant atom, that there should be an atom but it had been removed. But here, we have all atoms in their sites, but for some reason we are trying to enforce another extra atom. This is an excess atom, another extra atom that it will be squeezed between the different atoms. We squeeze within the gaps between the atom. Like for example, in this case, there should be a gap here. We are going to enforce an atom between this small gap. So this atom, when it is inserted, so it is interstitial, we are inserting an atom within these different lattice sites. So the vacant, it means that we are removing. Interstitial, it means that we are adding, we are inserting by force another atom to be squeezed within the gaps between the atoms. Make sense? So this is very quick, this is the difference between the vacant atoms and the interstitial atom as a defect. We do have another type, which is substitutional atom, just to know the difference between the three types. The substitutional atom, it is from the title, from the name. Substitutional atom, it means that one atom is going to replace another atom. Like you're going to remove atom of the original material and you're going to add another atom in place of this atom. So you are substituting, you are replacing two atoms together. This is going to give us the substitutional atoms. All of these types of defects, these are three different forms of defects, and they will result in different properties and changes in the properties of the material. But all of them are related to whatever one atom is missing. One atom will be enforced into the gaps between the atoms, or one atom is going to replace another atom. So they are related to the atoms. So that's why they are counted as point defect. Atom is just a point. So that's why they are named as point defects. Make sense? So again, the vacancy atom, it is one atom that is missing in the lattice site. And this will result in some distortion in the planes as already shown in this schematic. This atom or this type of defect, it do exist in all crystalline solids, whatever they are. Anyway, any solid material should have a certain number of vacant atoms. How we can calculate this number? This can be calculated using this formula. So this formula or equation, this calculates how many vacant atoms that should be exist within any material in the ideal condition, in the conventional condition as a real material. So this NV stands for the equilibrium number of vacancies or defect. This is, just to make it easy for you, this NV, this is the number of the vacant atoms. As we mentioned, any material should have a certain number of vacant atoms. Even if it is at room temperature in the conventional condition, it will have this such defect. So how many atoms that will be vacant or missing, the count of these missing atoms is NV. So NV stands for the number of vacancies or defects or vacant atoms, which is known as the equilibrium number of vacancies. Divided or equal, you can simply multiply this n times the exponential. So this, like, n stands for the number of potential defect sites or the number of lattice sites. We said that what is the lattice site? Like this atom, it fills into a lattice site. This atom fills into another lattice site, another lattice site. So every atom fills into its own lattice site. So every atom represent a lattice site, So the number of lattice site definitely or intuitively is going to be related to the number of atoms within the crystal or the material structure. You got it? Because every atom represents a lattice site. So this n, uppercase n, stands for the number of potential defect sites or number of lattice sites in general, which means the number of atoms that would be exist inside the material. And NV, this is the number of the missing atoms. Like you should have within this material structure a certain number of atoms, which is uppercase N. But NV, these are the number of the missing atoms, which are the vacant atoms. Make sense? This equal to the exponential, which e to the power of negative QV over KT. What is QV? This QV is known as the activation energy. What is the activation energy? Just to understand it, this activation energy, this is the amount of energy that we have to give to this material to remove an atom. But the question is, how can we remove an atom? This atom, as we discussed in chapter 2 or even chapter 3, you should have like one atom here, another atom there, and there should be another atom in the middle. And there should be some atoms surrounding it, right? There should be some interaction energy that is going and bonding force that is going to generate between all of these atoms. As we discussed in chapter 2, there should be some bonding force here, and this atom is bonded to this atom, is bonded to this atom, is bonded to this atom. So there are some bonding forces and some other interaction generated. This is what makes this atom squeezed or confined between these other 4 atoms. So for some reason, if you are interested in removing one of these atoms, to remove the atom, we have to break these bonds first. So to remove this atom, we have to break this bond, we have to break this bond, we have to break this bond and this one, then we can remove the atom. To break the bond, you should exert some energy. This amount of energy that is related or needed to break this, and it will be responsible for removing an atom or creating a vacant atom or creating a vacant lattice site is known as the activation energy. So again, the activation energy, this is the energy needed to create or to generate a vacant atom, to remove an atom. How? By breaking bonds. We have to break the bonds first. This amount of energy needed is known as QV, and this QV, which is the activation energy, it is a material property. It is different from one material type to another material type. Why? Because it do depend on the bonding between these atoms. And as we discussed in chapter 2, the bonding force, it is a material property that is different from one material to another material. Make sense? So simply, the NV, this stands for the number of the vacant atoms, how many vacant atoms that would be exist inside the material structure. N stands for all the number of atoms, in case that we do have a perfect material structure. Assuming that you do have a perfect material structure, assuming that all atoms are there. But anyway, there should be some vacant atom, which is NV. Equal the exponential of the negative. This negative is fixed in this expression, is fixed into this equation, divided by KT. K is known as Boltzmann's constant. T, this is the temperature. So why we are involving the temperature here? Because the easiest way to break a bond is to heat the material, right? As we discussed even in chapter 3, how we can break, or chapter 2, how we can break a bond. Your objective is just to melt the material. Melting the material or heating the material, increasing the temperature, weakens the bond. Weaken the bond, or it would reach into completely break the bond. So at certain temperature, some of the atoms will be, the bonding between them will be broken, and in that case, there are more vacancies who is going to generate up on increasing the temperature. So we should understand that the equilibrium number of vacancies, that this number of vacancies, this NV, depends on the temperature, and it increases as the temperature increases. As we heat the material, it means that there are more vacant atoms that is going to generate. There are more atoms that will be removed. There are more bonds that is going to be broken, and more vacant will be generated. Make sense? So that's why this temperature is located in the denominator, and we don't have this negative. Why? Because as we increasing the temperature, this term entirely will be decreasing. And since it is exponential, and this exponential it is negative, so as this value decreases, the value of the NV will increase. And that's why as this temperature increase, the NV, the number of the vacant atom, will be increasing. So again, as we increasing the temperature, more vacant atoms will be removed from the material structure. What is K? This is constant, known as the Boltzmann's constant, which is equal to the 1.38 times 10 to the power negative 23 joules per atom Kelvin, in case that this activation energy was given in joules, because energy, joule, it is a measure of energy. So in case that the activation energy was given to you in terms of joules, so directly this K will be 1.38 times 10 to the power negative 23 joules atom times Kelvin. It means that this temperature, it should be in Kelvin. Or it could be 8.62 times 10 to the power negative 5 in case that it was given as electron volt, which is like related to the electron charge, which is also a measure of the energy. This is another unit of the energy, which is different somehow than the joule. Joule, this is the mechanical concept of the energy, but EV, this is the energy which is associated to the electron's movement. So anyway, forget about this EV. It is anyway in case that the activation energy was given in EV. So in that case, you should substitute for K equals 8.62 times 10 to the power negative 5. These two numbers, you have to memorize them, and you're going to use them depending on the given activation energy. Make sense? So this expression simply how we can theoretically calculate the number of the vacant atoms depending on what? Depending on the temperature. It means that as we are increasing the temperature, the number of vacant atoms will be increasing. Make sense? Alright, so let us consider this example as a practice over using this expression to calculate the number of vacancies or equilibrium number of vacancies per cubic meter for copper at 1000 degrees Celsius. So calculate the equilibrium number of vacancies, which is NV per cubic meter. Per cubic meter, it means per meter cube. For copper at 1000 degrees Celsius, the energy for vacancy formation is 0.9 EV per atom. This is the QV. This EV per atom, this is the QV, is already given by 0.9 EV per atom. Again, this is the energy needed to form one vacant atom, to break the bonds to create one vacant atom. The atomic weight and density at this degree Celsius for copper were given by the 63.5 gram per mole, and the density was given by 8.4 gram per centimeter cubes respectively. It is required again to calculate the NV. So according to this expression, NV equals N times this exponential term. So NV equals N. What is N again? This is the total number of atoms that would be exist within the lattice site or within the crystal structure times the exponential of the negative QV divided by KT, uppercase. Make sense? So the first thing that we should calculate is N, uppercase. This N stands for the total number of atoms. You can deal with it like this is the total number of atoms that would be exist in the crystal structure. But this requires a volume. So here it is required to calculate the NV per unit volume per cubic meter. It means that we are interested in calculating, assume that you have a material, and this material form a crystal. This crystal, the volume of this crystal entirely, it is 1 meter cube. It is 1 meter cube. So within this 1 meter cube, how many vacant atoms? This is NV that we are interested in calculating. So it means that we are interested in calculating N. This N, it should equal to the number of atoms that would exist in this 1 meter cube of volume of this crystal. If you remember from chapter 3, we explained that the theoretical density, it equals N times the atomic number divided by the volume of the crystal. Divided by the volume of the crystal times the Avogadro's number. If you remember this expression from chapter 3. So simply, if I consider what should be the unit of these two terms, N over V. N, this is atom number of atoms per unit, per the volume of the unit crystal. This, for example, if this was like FCC crystal structure, we substitute for this N as 4. And this was the volume of this unit cell. So the unit of N over Vc, this is equivalent to atom per meter cube, because the volume should be in meter cube, the N it is count. So it is number of atoms per unit volume. And this is what we need. This atom per unit volume, this number of atom per unit volume, this is in uppercase that we are seeking here. So this in uppercase, it is originally N per unit volume, which we needed. So simply, if we can calculate, we can isolate this term N over V, and we substitute for this N over V as N uppercase and move it to the other side and divide by rho, you're gonna end up with this expression. So this expression, which is N equals rho times NA over A, this is what we drive it and we discussed before in chapter 3. So simply moving this one here to the left and then divide by rho, this is gonna give us N equals, or you're gonna just cross multiplication, you're gonna end up with rho times the Avogadro's number, which is Na divided by A. So this A, this is the atomic weight. This is the atomic weight of the material that is already given to us by 63.5 grams per mole. This is the atomic weight of this copper, of this material. It is well known, there is a material property known for any material. This Na, which is Avogadro's number, we said that this number it is 6.023 times 10 to the power 23. You have to memorize this number. This is the how many atoms that would exist per 1 mole of this material. Rho, this is the density which is already given to us by 8.4 gram per centimeter cube. So simply, we're gonna substitute with all the data that we have, like N equals rho, it is given by 8.4 times the Avogadro's number, which is this value, 6.023 times 10 to the power 23 divided by the atomic weight, which is 63.5. This is gonna give us the N, but we have to achieve some consistency into the units. So if we did the calculations by this of this number, this is gonna give us a value 8 times 10 to the power 22 atoms per meter cube. Why atoms? This is how many atoms that would exist in per centimeter cube. Centimeter cube. So if I substitute with the values as given to me to us, like 8.4, which is this gram per centimeter cube, and the Avogadro's number, then I divide it by joule per meter cube per mole, which is 63.5. This is gonna give us 8 times 10 to the power 22 atom number of atoms per centimeter cube. Assuming that you'd have 1 centimeter cube of this material, how many atoms that should be there? They should be 8 times 10 to the power 22 atoms. But remember that we needed in per cubic meter. It is required per cubic meter. So this means that I should convert the centimeter cube into meter cube. How we can convert? You need to multiply this number times 10 to the power 6 to convert from the centimeter cube to the meter cube. So this is going to give us 8 times 10 to the power 22 times 10 to the power 6. This is going to give us 8 times 10 to the power 28. Number of atoms divided by meter cube. So this is going to give you in 1 meter cube of this material, there should be 8 times 10 to the power 28 atoms there. But unfortunately, some of these atoms, some of these 8 times 10, 28 atoms are missing. How many atoms are missing? This is the number of the vacant atoms or the equilibrium number of vacancies, which is NV, that we need to calculate it. How we can calculate it? You should use this expression. So what we have done so far, we just calculated N, the number of atoms that would be exist in 1 meter cube of this material. Then your objective is just to plug the other data. Everything we have it now. So it's simply NV, which is the number of the vacant atoms, equals N that we just calculated, times the exponential of the negative QV, which is the activation energy, which is this energy needed to create a vacant atom, is given by 0.9 eV per atom. So it is 0.9. You're just going to substitute 0.9 divided by K times T. T, this is the temperature. It is given as 1000 degrees Celsius, but it should be converted into Kelvin. How we can convert from Celsius to Kelvin? Add plus 273. So this is going to give us this value. It should be 1000 plus 273. You're going to end up with 1273 Kelvin. So we have to convert. We have to substitute by the temperature in terms of kelvins here, as already given. Then you're just going to plug the K, which is Boltzmann constant, which is 8.62 times 10 to the power negative 5. Why we substituted by this value? Because the QV was given in EV. So in that case, you have to use the 8.62 times 10 to the power negative 5. Do the multiplications. You're going to end up with the number of the vacant atom will be 2.2 times 10 to the power 25 number of atoms per meter cube. It means that if you have 1 meter cube material, there should be 8 times 10 to the power 28 atoms there. But if we heated this material at 1000 degrees Celsius or 1273 Kelvin, there should be some vacant atom that will be created. The number of this vacant atom will be 2.2 times 10 to the power 25 atoms will be missing in that case as vacant atoms. Make sense? So generally speaking, even at room temperature, even if you substitute for T by the room temperature, you're gonna almost end up with a specific value or number of the vacant atom. It means that even at room temperature, there would be some vacant atom that would be created within the material. So this type of defect, this is the first type of defect of the point defects. We have 3 types as point defect. This is the first of them. Vacant atom, missing atom. It do exist in all cases, in all crystalline solid material, even in the conventional case. And the number of the vacant atom depend on the temperature, and this is according to this expression and this example. So how we can calculate or determine the activation energy, which is QV, for a certain material experimental. Using an experimental method, how we can determine this QV. As I mentioned, this QV, this is the amount of energy needed to create a vacant, and this is like a kind of material property. It will be different from one material to the other material. Why? Because this is the energy needed to break the bond. And the bond itself, it is a material property. It changes from one material to the other material. The strength of this bond between the atoms, it is different from one material to the other material. So that's why this QV also is a material property. How we can determine this QV experimentally. So the procedure is simple, that we are getting an image. Like we're gonna look to the material atomic structure through the TM, this TM transmission electron microscope. This is high resolution microscope that we can observe and see, clearly see the distribution of atoms inside the material microstructure. So we're gonna choose a certain piece of this material, like a material sample, a sample of the material, and we're gonna look at it through this microscope, and we're gonna have multiple or different images of this microstructure. So initially, we're going to have this material at room temperature, for example. Then we're going to have an image of this material microstructure. Then by the naked eye, we are going to start to count, because we zoomed into the material microstructure, so we can clearly see these atoms. So we can count how many vacant lattice, how many empty spaces that would exist between these different atoms. Again, we're gonna see and observe these atoms, inside the material structure through the microscope, through the TM, then we're gonna count how many vacant atoms that would be located within this area. This area should include a certain number of atoms in case that it was perfect. But anyway, there should be a certain number of vacant atoms. So we're gonna count how many atoms that would be exist within this TM, and then we're gonna count how many vacant atoms that would be exist. It could be difficult to you, or it could be, for example, there are some software that we can do processing to the images that we receive from the TM. We can do processing to these images and using some software like the ImageJ, for example, and using this software, we can count how many vacant atoms, and the software automatically gonna count the number of the lattices that should be there. And also the software gonna give us directly the NV, the number of vacant atoms, how much they are. So instead of counting by yourself, you can use one of the software that currently used for as image processing for these images that we drive from the TM to calculate NV and M and N. Then we can divide these two numbers as given here, NV over N, and we're gonna draw over a curve, create a curve at a certain temperature. So initially we tested, or we looked to this material through the TM while this material was at room temperature. Then we're gonna have another material sample of the same material but at a higher temperature. Then we're gonna look at it through the TM. Then we're gonna count how many NV and N, and we divide this ratio together and record this value. Then we're gonna heat more, increase the temperature, heat the material more, and have another sample and look at it through the TM, count how many NV and N, then heat more, and so repeat at different temperatures. Then we can create this curve, generate this curve between the NV over N versus T. So this is gonna give us like a curve, exponential increase with the temperature as the temperature increases. As we discussed, as you increase the temperature, the number of the vacant atoms is going to increase. How we can find QV then? From this figure, if we converted this vertical axis into the natural logarithmic value, and instead of plotting this NV over N, we're gonna plot the ln, which is the natural logarithmic of the NV over N versus 1 over T. This is gonna end up with like almost a straight curve, a straight line. Then we can calculate the slope of this straight line. The slope as shown from mathematics, any line that goes from the second quadrant to the third quadrant, or the fourth quadrant, I'm sorry, from the second to the fourth, is gonna be with a negative slope. So that's why we are getting negative into this expression. Why? Indicating that we do have a decay at the temperature, or increase as the temperature increases. So the slope of this curve, this is gonna give us Q over K, and remember K, this is the Boltzmann constant, which is a constant value. Then you can directly determine QV, how much it is. So this is how we can determine this QV experimentally. This is just for your information to know how we can drive this QV, and to prove to you that this QV, it is a material property that we can measure. And even I explain to you the procedure, how we basically do using the TM, how we can drive this QV. Make sense? So this is for the vacant atoms. Now let us to move to another defect, the second type of the point defect, which is interstitials. Interstitials, it could be self-interstitial, and this is the first thing that we are going to discuss. What does it mean, self-interstitial? It means that you are going to enforce an atom of the same material. Like you do have all of these atoms forming the same material, and assume that this material, it is a pure material, one element. So, and you're gonna have one extra atom of the same type, that it will be squeezed into the gap, inserted into the gap between these atoms. This is known as self-interstitials. Self-interstitials. So instead of having a vacant atom, and instead of that, you're gonna have extra atoms added. But this not likely to happen. This is barely you're gonna have a material with self-interstition. In the conventional case, the material should have vacant atoms. In many of the cases, the material will be with a vacant atom. There will not be any excess or extra atoms. But this is a special type of defect that would exist in some special cases, which are rare cases. Barely you can observe or find this type of defect in any material, especially the self-interstitial atom. So a self-interstitial, it is an atom, extra atom from the same crystal that is positioned between atom sites. Like this is an atom site, another atom site, atom site, atom site. You're gonna squeeze something in the middle. As shown here, once we squeeze this atom, self-interstitial, this atom between these atom sites, this definitely is going to result in some distortion into these crystallographic planes, into these planes of atoms. And instead of having these planes straight, they're going to be like curved next or around this interstitial, indicating that there is a defect. This defect will result in some changes in the material properties, and this is what will be discussed in detail in the next chapters. Make sense? So that's why here we are just discussing these different forms and types of defects. What are their influence over the material properties and how they do affect the material properties, this will be discussed later in another chapter. The formation of this defect is not highly possible. Why? The reason because the atoms is larger than the interstitial position in which it's supposed to be positioned in. Since we are talking about self-interstitial, usually the gap, because interstitial, it means that this atom, it should be squeezed into the gap between the atoms. It will not replace. If it's going to replace an atom, remove one and add another one, this is known as substitutional. This is another defect. But the interstitial, it means that we have to enforce an atom into the gap between these lattices. So since we are talking about self, it means that the atom that it will be inserted, it will be of the atom type. In that case, the size of the atom in many of the cases is likely to be larger than this gap between this atom. There should be a gap here, a gap here. So the size of the atom will be bigger. So it will be difficult. To do so, this required a very high energy to do so. This requires a very high energy to achieve self-interstitial. So it would be easy for the material to create a vacant atom more than having a self-interstitial atom. So that's why it is barely happening in any material that you're going to have this self-interstitial. The reason is because the atom is larger than the interstitial position or the gap between atoms in which it's supposed to be positioned in or inserted in. Make sense? So since we are talking about interstitials, this brings to us the impurities in solids and the alloying. We discussed before what is the alloy. Alloy, it is a chemical compound of metal and non-metal. Alloy, it is mainly a metal with some impurities. So again, the alloy, it is a metal material. Alloy, it is a metal material. But as we mentioned before, in many of the cases, metals are exist in the form of an alloy. It is difficult to have 100% pure metal. Like for example, aluminum. It is difficult to have 100% aluminum material. Anyway, there should be some impurities that it will be inserted inside the material structure. So you could have, for example, 99% of the material, of the atoms, 99% of the atoms are aluminum, and you're going to have only 1% of the material microstructure of another material. So there is no 100% pure material. It is impossible. Anyway, there should be some certain of impurities that would be exist, especially when we talk about metallic material, metals. So these impurities make the metal to be in the form of an alloy. So the alloy, it is metal with impurities. This is how we can understand the alloy. This is one of the things. So it is impossible to have 100% pure metal. It is not possible. Pure metal consists only of one atomic type, as we discussed before. It should be one element, like pure aluminum, pure copper. Pure copper, yes, pure magnesium. Any type of metallic material which is 100%, it is impossible. Anyway, there should be some defects, some impurities. Metals usually contains impurities. And this what gives the alloy. The alloy is a chemical compound of metal and non-metals. In many of the cases, these impurities are non-metals, which will be inserted into the metal, inside the metal, with distributed randomly inside the atomic structure of the metal, mixed with the atoms of the metallic atoms to form an alloy. The non-metal atoms are impurities, represent impurities with a very small fraction, as we mentioned before, that we intentionally add them. Alloying, this is an industry, this is a manufacturing method of making material or metal better. Alloying gives better properties to the material, as it will be discussed over the next chapters. Inserting these impurities adds value to this material. Like you add a salt to your dish or to your food. Without the salt, you can eat it, yes, but it is not delicious as if you added some salt to it. So this salt, these impurities gives value to this metallic material. Metal material, pure metal by itself, it is a very weak material. It is not preferred in terms of engineering. But adding these few fractions of impurities will enhance the properties of this material way better, and that's why it is more expensive even. Alloy is more expensive than pure metal. A typical example of this, the copper, the iron and the steel. Iron, it is Fe. If you do have a pure iron, 100% iron, it is a very weak material. But if we added, let's say, like 1% of carbon to this iron, you're gonna end up with a steel. Steel, it is much more stronger than iron. Just 1% of carbon, even 0.05% of carbon is going to enhance the properties of the iron to make it steel. So steel, it is an alloy. But Fe, it is pure metal. Fe, this is pure iron, 100% iron, it is weak. We're barely using it. We are not using iron in any engineering application. And instead, we are using steel. Steel, it is iron plus a very small amount of impurities. One of these impurities could be carbon. But in addition to the carbon, we can add any other elements to it to give more property. For example, if we added to the iron and carbon, we added cobalt, this is going to give us stainless steel, for example. The stainless steel, this is one of the types of the steel which can avoid or can withstand the stains. So all of these impurities, when we add them to the pure material, this gives value to this material, to the metal, and make this material more expensive. Steel, it is much more expensive than Fe, than the pure metal. Make sense? So this is the value of the alloying. So alloying, simply, it is a pure material, and then you're going to add some impurities into this material with the aim of enhancing its properties, like the case of iron and steel. So it is a chemical composition between metal and non-metal. The fraction of the non-metal, it is very negligible. Few things which will be counted as impurities, which we intentionally add to impart some specific characteristics and properties to the metal. Alloying is the process of adding these properties. What does it mean, alloying? It is a manufacturing method that depend on chemical interaction. Like we are adding, we have, for example, how we can make steel. In steel making, we should bring this Fe iron and we're gonna melt it completely. Then we are going to add these impurities to it while it is in the liquid state. Then we're gonna leave it and we're gonna solidify this Fe to end up with the steel. While we adding these chemical things, when we adding this carbon and these impurities, there should be some chemical interaction that is gonna take place. This chemical interaction will result in an alloy. So that's why we said that the alloy, it is a chemical compound. There should be a chemical interaction. And this is what distinguishes alloy from a composite material, as we discussed before. Alloying is the process of making this alloy. Is the process of adding this impurity to the metal to form a solid solution. So the alloy, when we add, you have a pure metal. Then you're going to add impurity, you're going to end up with a solid solution. Solid solution, like the chemical guys, engineer, they are creating these solid solutions or this solution. Solution, it means that you are mixing chemically mixing two material to end up with a new material. It means that this alloy, which is steel, is totally different than the original material. It's totally different than copper, than iron or carbon. Steel, it is not carbon. Steel, it is not iron. But it is the chemical composition. It is the alloy of iron plus carbon. So it is a new material, a new solid solution, this new material that is going to form, which it will be counted as alloy, is known as the solid solution in general of better properties. So this is the meaning of alloying. Alloying is the process of adding the impurity with the aim of enhancing the properties of metal, and this will result in a solid solution of better properties. So what is a solid solution then? This is the new solid, this is the new alloy, this is the new material that is going to be generated or formed due to the insertion or the addition of impurities inside the structure of a hosting material. For the alloying process, what will be the hosting material will be metal. Remember that alloying is happening only for metals. There is no alloying for ceramics or polymers. We said that metals, three types in nature: metals, ceramics, polymers. There is no alloying for polymers, there is no alloying for ceramics. Alloying only for metals. So when we talk about alloying, the alloy, it is a solid solution in general. Solid solution, this is a general expression. Alloy, it is a solid solution. In that case, the hosting material will be the metal and the impurity will be the carbon, for example. The other impurities, the other non-metals that we are going to add to this metallic material, this will result in a solid solution. So this is the new alloy, the new solid that is going to form due to the insertion of impurities inside the structure of the hosting material. The crystal structure of the hosting material is maintained, and this is a key condition, is maintained to end up with a solid solution, and no new structures are formed. What does it mean, this statement? And this is very important. This what distinguishes the solid solution, for example, from another phase, a new phase. These are two different things. Solid solution, it means that we do have a hosting material like metal, and then we're going to add a few fractions of the impurity, like iron and copper. These impurities will be inserted somehow, and we are going to explain how we are going to add these impurities. But anyway, these impurities will be added and inserted inside the atoms and arranged or distributed with the atoms of the hosting material, the original material, the metal material. This will result into a new material, but there is no change in the crystal structure. Like, for example, what is the crystal structure of aluminum? As we discussed in chapter 3, it is FCC crystal structure. This FCC crystal structure of the pure aluminum, when we add any impurity to it, it will not change. If it is not a change, this is going to end up with a solid solution. But for some reason, if this crystal structure has changed, this will result into a new phase. So there is a difference between a new phase and a new solid solution. Solid solution, it means that the original crystal structure of the hosting material, it will be maintained, it will be preserved, it will not be changing. It will be still the same. FCC will be FCC after we add the impurity. FCC before the addition of the impurity, once we add it will be FCC, the same crystal structure, yes? So this is solid solution. But if the crystal structure had been changed, this will not be counted a solid solution. It will be counted a new phase, like a new material, totally different material. And this is what is happening. This is the difference between ceramic, for example, and alloy. Alloy, it is a chemical compound of metal and non-metal. Ceramic material, if you refer to chapter 1, the definition of ceramic material, it is a chemical compound of metal and non-metal. So what is the difference between ceramic and metal and alloy? The difference is in alloy, the percent of the non-metal, it is too small. So when we add these few fractions of the non-metal, this will not change the crystal structure of the original metal material, and this will result in a solid solution which will be counted as an alloy. But in the ceramic material, the fraction of the non-metal is high. So this definitely will result in a change in the crystal structure. And this will gonna result in another material which will be counted as ceramic non-metal. It will not be counted metal anymore. Alloy is still metal. But the ceramic material, the percent of the non-metal part or impurities, it is high fraction, and this will result into change in the crystal structure. So that's why we're going to end up with a different material. That's why we studied in chapter 3 the crystal structure. because all the properties are related to the specific crystal structure of material. If we change it, this material structure, we are changing the material entirely. We are changing everything in this material, and we even talking about another material. And this what distinguishes the solid solution from a new phase. So, and this is already explained here. So the solid solution versus the new solid phase. Solid solution and new phase. New solid solution and a new phase. In a solid solution, the crystal structure of the solvent, which is the hosting material, is not altered, doesn't change. It will be maintained, and the solute, which is the atom or the impurity that will be added, are randomly distributed inside the crystal structure. There is no change in the crystal structure, but instead we're just going to add some impurity atoms. But the new solid phase is the formation of a new crystal structure up on the addition of the new impurities. You're going to end up with a new crystal structure, and this is the difference between solid solution and new solid phase. Make sense? So, what is a solvent and solute? The solvent, this is the hosting material. This is like the metal, like the iron. This is the material that is going to host the other impurities, or the material that is affected with the impurities. The material with the highest concentration. This is the material that has higher percent inside the material structure, is known as the solvent. This is the hosting material like metal. Solute, these are the impurities which will be inserted in the atomic structure of the hosting material. It has the lower concentration. This is just to know the difference between solvent and solute, and I'm pretty sure that the mechanical engineer, they do have an idea about the solvent and solute, because they are using and creating these and generating these solid solutions. So solid solution, it requires a chemical interaction between two different materials, solvent and solute, to end up with a new solid solution. But the key condition is that the crystal structure is still the same. But if the crystal structure has changed, we're going to end up with a new phase, which is like a new different material. Make sense? And this is what distinguishes alloying from making ceramic material. Make sense? So the question is how these impurities are added to make a new solid solution or a new material. We said that there are two possibilities here. In case that the fraction of these impurities, it is not that big, you're going to end up with an alloy. You're going to end up with a solid solution. There is no changes in the crystal structure of the original material, of the host material, of the solvent. This is one option. The other option, in case that the percent of the impurities is high, this will result in a new phase. New material that is going to be generated, a change in the crystal structure. So there are two scenarios. Either there is no change in the crystal structure, or there is a change by the addition of the impurities. So that's why the addition of the impurities to a pure metal results in two options. One option, only solid solution will be formed. This means there is no change in the crystal structure. The other option is solid solution plus a new phase. It means that new phase, it means that there could be some different crystal structure is going to show up inside the material structure. Like in this case, you may have the original crystal structure still maintained, but some parts will be of a different crystal structure. So this will be counted as solid solution with embedded new phase. So this is going to give like a new material, like a new ceramic material. It will not be counted anymore as alloy or as metal. Make sense? It is more likely to be ceramic material, which will result, this is in case that you're going to end up with a solid solution and there should be some new phases, a different crystal structure that is going to form inside the material structure. So for the first case, in case that we are going to add these impurities and we're going to end up with a solid solution with no changes into the crystal structure, how these impurities will be added? There are two options. This impurity could be added as interstitial solid solution, as interstitial. What does it mean? In case that the impurity, the size of the atom of the impurity is too small in comparison to the size of the hosting material atom. We have hosting material, which is solvent. We have solute, which is the impurity. In case, for example, like in case that carbon that will be inserted into Fe, which is iron. This gray atoms, these are the Fe iron. These are the Fe iron. It is huge iron. The size of the atom, it is big. In comparison to the size or the diameter of the carbon atom it is too small. So when we add a small fraction of the carbon, it will not be able to replace the Fe ion, but it will be inserted into the gaps between the atoms, between this lattice site. The insertion of an atom between the gaps, this is known as interstitial, and this is the second defect that we discussed. But here we discussed the self-interstitial. Interstitial in general, it means that you are going to insert an atom, whatever of the same atom type or a different atom type, between the gaps. The gap within the gap that exists between these atoms. If it is of the same type, it will be self-interstitial. If it is of a different type, it will be interstitial solid solution or interstitial of a different material, which is likely to be impurity like carbon, will be inserted into the vacuums or the gaps between the atom sites of the Fe ion, which is iron. The other option is that how about if the size of the atom of the impurity, it is big enough, very close to the size of the atom of the host material, like the case of copper and nickel. So the dark atoms, these are the nickel, and this yellow or orange, these are brown, these are the copper atom. As you can see, the size of the copper atom, it is very close to the nickel atom. So it means that this carbon, it will not be able to be squeezed into the gaps between the atoms. So it means that to add the copper, we have to remove a nickel atom and replace this nickel atom with a copper atom. And this is what results in a substitutional solid solution. So the solid solution or the alloy that it will be generated, it could be generated by interstitials or by substitutionals. Interstitial in case that the size of the atom in comparison to the size of the hosting material atom, it is too small, so it will be squeezed into the gap, so this will be counted as interstitial solid solution or interstitial alloy. Or in case that the difference between the sizes of the host and the solvent, the host and the impurity atoms, it is not that big, in that case impurity atoms should replace the hosting material atom, and this will result in a substitutional solid solution. So this is how we can add the impurity. It would be either interstitial or substitutional. So the substitutional solid solution in which the solute, which are the impurity atoms, substitute the hosting material. So that's why we got the name as substitution solid solution, and this is one of the defects. This is the third type of defect. We said that we have three defects. We do have vacant atom, we do have interstitial atom, we do have substitutional atom. So the substitutional, it shows up in case that we are adding impurity of an atom that almost have the same size or diameter of the hosting material atom. So in that case, we have to replace atoms, and that's why we're going to end up with substitutional solid solution. Or interstitial solid solution, in which the solute or the impurity atoms are inserted between the atomic sites within the atom, and this definitely depends first of all on the count or the size of the atom itself. The crystal structure of the hosting material is not altered. Impurities are randomly distributed, this to end up with a solid solution. But as I said, in case that we end up with some changes into the crystal structure, this is going to give us a new phase. Like you may add the impurities to create an alloy, and for some reason you're going to find part of this material structure will have a different arrangement of atom, indicating a different crystal structure. Refer to chapter 3. We said that in chapter 3, the crystal structure, what does it mean? It is how we are arranging atoms. If atoms will be arranged differently, this indicates a different crystal structure. So as you can see, this gray and orange atoms, they do have a specific arrangement everywhere except within this part. Within this part, which is circled here, atoms, they do have both atoms, the gray atoms, which are the solvent, and the solute atoms, both they do have a different arrangement, forming another crystal structure. So this different thing form another phase inside the material, or with a different composition, often different crystal structure, which form a new phase inside this material structure. So again, how we can do alloys or adding impurities to the material could result into a new phase or a solid solution. How we can create this solid solution, it would be substitutional or interstitial. Make sense? In case that we're going to end up with a different crystal structure, this is going to form a new phase inside the material structure, which indicate like a new material. Okay? Alright, so what are the conditions for the substitutional solid solution to be formed? As we mentioned here, one of the factors is the size of the atom. Like if the size of the atomic impurity, it is very small, we're gonna form interstitial solid solution, but it's gonna be substitutional solid solution in case that the difference between the atomic sizes, it is not that big, so it should be substitutional. So the question is, what are the conditions in general that would be needed to achieve substitutional solid solution? Interstitial solid solution, it is more likely to happen. This interstitial, it is more likely to happen than the substitutional solid solution. To substitute an atom with another atom, it is not that easy. This requires some certain conditions that allow the existence or the happening or the occurrence of this substitutional solid solution. These conditions are 4 conditions based on which we can judge whatever these two materials, they can dissolve to each other or they can form substitutional solid solution or not. One factor is the atomic size factor. As we mentioned, in case that the difference between the atoms size, the atom sizes, it is not that big, it is more likely to be substitutional. So if the difference in the atomic radii or the atomic radius of the two atoms is less than 15%, a substitutional solid solution of the two atoms will form. So again, if the difference in the diameters or the radius of the two atoms is less than 15%, this indicates that there is a substitutional solid solution that can take place. The other condition is crystal structure. If the two atoms are of the same crystal structure, a substitutional solid solution will form. It is more likely to form in case that both they do have the same crystal structure. But how about if they don't have the same crystal structure? You could consider or measure over the other conditions, but this is one of the conditions that in case that they do have the same crystal structure, they're gonna be likely to be forming. But for example, if you do have one metal with FCC crystal structure and the other impurity, it is also FCC crystal structure, so it is likely to be substitutional. But how about if you do have FCC with BCC? There could be a substitutional that it could be happening in that case, and we can form a substitutional solution, but it is not likely to be happening. It means that it would be difficult. It is not that easy. We require to exert some more energy and effort to create such a substitutional solution. Why? Because of the difference in the crystal structure. How about if you do have FCC and HCB? The difference between the FCC and HCB, it is too big difference in the crystal structure. So it becomes more and more difficult. But the difference between FCC crystal structure and BCC crystal structure, there is no big difference as long as they belong to the same crystal system. If you remember from chapter 3, both are cubic. So they can form substitution solution, but it is not that easy. It becomes more difficult in case that you have a cubic crystal structure and a hexagonal crystal structure. Make sense? So in case that the crystal structure are identical, this is the best option. The substitution solution is going to be likely, it can be simply formed. Also, the electronegativity or proximity in the periodic table. What are these things? These are related to the number of the atoms, electrons, and the number of the orbits around the nucleus of the atom. It is related to the structure of the atom somehow. I won't gonna go through details. I'm pretty sure that the chemical engineer, they are aware of this electronegativity things, but this could be something unknown to the mechanical engineer, but that is fine. It is a measure. which is related to the periodic table or the location of the element within the periodic table that depend on the number of electrons and the how many electrons that could be located at the outer shell, and the ability of the element to share its electron with some other elements or atoms. All of this related to the electronegativity. So it is more related to something or to the structure of the atom of this element. So it is a measure, it is a number that is well known for all elements. In case if the two atoms have the same electronegativity number, if this number is the same or very close between these two atoms, so they can easily form a substitutional solid solution. But if this number is different, the difference between this number is huge, so there would be a difficulty on achieving a substitutional solid solution by these two atoms or these two materials. Also the valences. The valences, this is the free electrons or the electron that located at the outer shell of this atom, as we discussed over chapter 2. So the valences, they count how many valent electrons that would be exist at the outer shell of the metal. This also a factor. A metal will have a greater tendency to dissolve or to form a substitutional solid solution another metal if a higher valence than the one with lower valences. So what does it mean? In case that you do have one atom, like you do have a material, and there are two candidates as impurities, which one can be dissolved easy in comparison to the other one with this material? This depends on the number of the valence atom that would be exist at the outer shell of these two atoms. So if the number of valences here is 3 and here it is 2, this 3, it is bigger than 2. This one is more likely to be dissolved. The one with higher number of valences will be likely to be dissolved and form substitutional solid solution than the other one. So as we are increasing the number of the valence electrons at the outer shell of the atom, this gonna increase the possibility of forming a substitutional solid solution. So these are 4 conditions based on which we can judge whatever this substitutional solid or the formation or the achievement of this substitutional solid solution, it is easy or difficult. Or in case that we are comparing between two candidates for this material, which one is going to be better to be dissolved within this material, this can be judged over these 4 conditions. So let us consider this example here and try to answer this question. Would predict more aluminum or silver? So the aluminum and silver, these are 2 candidates to dissolve in zinc. So the host material, the hosting material will be the zinc. The solvent will be the zinc. This is the one with the highest percent. And the impurities are aluminum or silver. These are 2 candidates. There are 2 possibilities. And we would like to examine which one can be easy dissolved within this solvent to form a substitutional solution than the other one. Is it aluminum or silver? You got it? So the solvent material will be the zinc. And we would like to compare between the aluminum and the silver. So we're gonna have like a comparison between the aluminum and the silver. Based on the 4 conditions, the first condition is the atomic size, the radius of the atom of every one of these atoms. So if we're gonna calculate the atomic size factor, this factor is gonna be the difference between the atomic radius of the zinc and the atomic radius of the aluminum. And also the atomic radius of the zinc and the atomic radius of the silver. So for example, the zinc, which is Zn, it has atomic radius of 0.1332. So this is the radius of the zinc. Negative the radius of the aluminum. So the radius of the aluminum is 0.143431. So this is of aluminum. Divided by the radius of the zinc times 100 to end up with a percent. We said that according to this condition, if the difference, so the difference it should be in the form of a percent between the radius of the host material negative the radius of the impurity divided by the radius of the host material times 100. This is going to give you the percent. If this percent less than 15%, it means that there is a substitutional solid solution that can be formed. So in that case, the difference here, when we calculate this, is going to give us a negative 7.43. Forget about the negative. I just compare the absolute value, the 7.43%. It is less than 15%. It means that the aluminum can be dissolved. It can form a substitutional solid solution with the zinc. How about the atomic size factor for the silver? The zinc is 0.1332. This is the radius for the zinc. The radius for the Ag it is 0.445. This is the aluminum, the radius of Ag divided by the radius of the zinc times 100. This is going to give us negative 8.483%, less than 15%. So it means that the atomic size for the Ag, it is also less than 15%. It means that it can achieve substitutional solid solution. So it means that there should be like 1 point to the aluminum and there is another point. The first condition, it is acceptable to both. But remember that the aluminum, it is more likely to be dissolved within the zinc more than the Ag. Why? Because the difference here, it is lower than the difference in the Ag case or the silver case. It means that this gives 1 point, one add to the aluminum over the Ag, but the difference, it is not that big. Here it is 7.43, here it is 8.48. It is not that big difference. Both, they can form substitutional solid solution based on this atomic size condition. This is only one condition. Then the second condition, which is the electronegativity. For example, the electronegativity of aluminum, it is 1.5. It is a number just for the aluminum. It will be given to you. But the one for the zinc, so this is for the zinc, it is 1.6. For the aluminum, it is 1.5. The difference, it is 0.1. It is lower than, but the difference, it is 0.1. The electronegativity of the silver, it is 1.9. It is lower than 1.6 for the zinc, and the difference, it is 0.3. So according to this condition of the electronegativity, as long as they do have the same number, which is not possible, it means that the difference have the same electronegativity, they can be easily substitute each other, or they can form a substitutional solid solution. So according to this indicates the aluminum, it is more dissolvent into the zinc more than the Ag. Why? The difference here, it is too small in comparison to the other one. It is 0.1, here it is 0.3. So this gives another add to the aluminum. The aluminum is going to be much more better than the silver to be solvent to form substitutional solid solution. The other conditions, so these are the condition number 3. The condition number 2, the crystal structure. How about the crystal structure of the aluminum? It is FCC, as shown here. The aluminum, it is FCC. And the crystal structure of the Ag, it is also FCC. So both, they are FCCs. While the zinc, it is HCB. So it means that both aluminum and Ag, they are even. They are not preferred to be solvent, to be dissolved with the zinc because of the difference in the crystal structure. The aluminum and the silver both have FCC. The zinc has HCB. So there is a difficulty based on the crystal structure to form a substitutional solid solution. But we can form this one. We can apply more energy and we can achieve this substitutional solid solution. Why? Because there is a difference in the crystal structure between the solvent and the solute, or the host material and the impurity. But both are even. The aluminum and the silver, both are even because both they do have the same crystal structure. So it means that we cannot judge which one is better based on the crystal structure. So it means that we're just going to add one add here, 1 point here, and 1 point here. Okay, still the aluminum, it is better. And the last condition, the fourth condition, the number of the valence electrons. It is plus 3, it is 3, 4 for the aluminum, but it is only 1 for the silver. It means that the aluminum, it is more dissolvent than the Ag. We said that as the number of the valence electron increases, this achieves better substitutional solid solution, or increases the possibility of forming a substitutional solid solution. It means that aluminum, it is more dissolvent into zinc more than the Ag. So this gives another point over the Ag to the aluminum. So as you can see, there are 4 points to the aluminum, but only 1 point to the Ag, which they were even. The aluminum, and according to the crystal structure, they were even. So we can even cancel this point with this point, this gives 3 adds or 3 conditions have been achieved more for the aluminum. This indicates that in general, the aluminum it is more dissolvent in zinc than the Eg, which is silver. Make sense? It means that to achieve a substitution solution for zinc, aluminum into zinc, it's going to be much more easy than achieving the same substitution solution between the zinc and the silver. The last example is would predict more zinc or aluminum to dissolve in copper, and why? So the copper will be the host material, will be the solvent, and the impurities will be either zinc or aluminum. And we would like to judge which can be dissolved easy in copper than the other opponent or the other material candidate. So we have 4 conditions. According to the first condition, which is the atomic size factor to the aluminum, it is the 0.278. This is the copper. We should identify the atomic radius of the copper, which is 0.1278. Negative the atomic radius of the aluminum, which is already given here by 0.143. Divided by the radius, the atomic radius of the host material. The host material is the copper. You should identify which is the material that it will be common. The host material, this is the copper. So the copper, the radius of the host material, negative the radius of the impurity divided by the radius of the host material times 100. This gives negative 11.97%. Don't forget about the sign, just deal with the absolute value. It is less than 15%, so we are in a good shape. The same thing, the atomic factor for the zinc. The radius for the zinc is 0.1332. So, and the radius, the atomic radius of the copper is 0.1278. Negative 0.1332 divided by the atomic radius of the copper times 100 gives negative 4.225%, which indicate that the zinc is more bitter than copper according to the atomic size factor. Both they can form substitution solution. Why? Because the atomic factor is less than, or the difference in the atomic radius, it is less than 15%. But still the zinc, when compared to the copper, the zinc will have 1 more point, 1 point over the copper. Why? Because the difference in the radius, it is too small in comparison to the radius difference in the copper. Make sense? It means that zinc has 1 more point. According to the electronegativity of the aluminum, it is 1.5, and the one for the copper, this is the electronegativity for the copper. These 2 values will be given, and the one for aluminum it is 1.5, so the difference is 0.4. The zinc, the electronegativity of the zinc, it is 1.6 less than 1.9, and the difference it is 0.3. So as you can see, we're going to add 1 more point to the zinc. Why? The difference in the electronegativity in the zinc in comparison to the aluminum, this makes the zinc it is more bitter to form substitution solution with the copper than the aluminum according to the electronegativity. But as you can see, the difference it is not that big. It is 0.3, 0.4. So the difference between the 2 numbers it is not that big, but still the Zn it is much more preferred according to the electronegativity. According to the crystal structure, and this is the big deal. The crystal structure of the aluminum, it is FCC, but the zinc, it is HCCB. But the crystal structure of the copper, it is FCC. As you can see, the crystal structure of the copper, FCC, the zinc, it is HCB, the aluminum, it is FCC. This makes the aluminum can be dissolved easy into the copper more than the zinc. The zinc, it is a totally different crystal structure than the host material, than the copper, but the aluminum, they do have the exact same crystal structure. This gives 1 more point to the copper over the zinc. I'm sorry, to the aluminum. We are comparing the aluminum and the zinc. The host material is the copper. So this gives 1 point to the aluminum over the zinc. We still need to compare the last condition. The last condition is the number of the valency, which are the free electron or the electron that located at the outermost shell. They are 3 in the aluminum and 2 in the zinc. This indicates, so the valence in the aluminum, it is 3, but in the zinc it is just 2. So this indicates that the aluminum is going to be much more dissolvent than the zinc in copper. This gives 1 more point to the aluminum. So as you can see, we got here 2 points according to these two conditions, the crystal structure and the valence for aluminum, and the other two conditions, the atomic structure and the electronegativity for the zinc, we got other 2 points. So they are even. This zinc, it is better in 2 conditions, and aluminum, it is better or preferred according to other 2 conditions. So the question is, which one will be dissolvent more than the other one into the color? The aluminum. Why? Because the crystal structure is a big deal. As you can see, the zinc is better according to the atomic radius and the electronegativity, but the aluminum, it is better according to the crystal structure and the valence. The crystal structure is a big deal. So if it is even, you can judge based on the crystal structure. As long as the difference in the crystal structure, it is huge. We do have here FCC and FCC for the copper. It is perfect thing to form substitution salt solution, but HCB and FCC to form a substitution salt solution, it is not that easy. The difference in the crystal structure is significant. Here it is hexagonal, there it is cubic. Even it is another hexagonal crystal structure, this is FCC. So the difference in the crystal structure, it is significant. That's why this add more value to the aluminum to be more dissolvent into the copper than the zinc. So that's why we're gonna say that the aluminum, it is more dissolvent in copper than the zinc. The reason is according to these 4 conditions. All right, so this is simply how, and this is the objective of today's video. That's it for today. The objective was just to discuss the buoyant impurities. We didn't discuss. We discussed in general what does it mean imperfection or a defect inside the material structure. We said that we do have 3 groups of defects or imperfections. We discussed the first group, which is buoyant defects. And we knew how we can. What does it mean? Vacancy atoms, mean that there are some missing atoms. Interstitial atoms, substitutional atoms. Also, we discussed these things in the context of the impurity and the alloying and how we can form a solid solution or a new phase. Also, we discussed the conditions that based on which we can judge whether we can form a substitution solid solution or not. These are the things that we have covered over today's video. So that's it for today, and thank you so much, and see you in the next video.